So, in our last video, we added the ability to calculate the probability of a cell containing a mine or not, using what looks like to be a reasonable technique. So this time we want to actually use these values to help drive our brute force algorithm. At the moment the brute force works just by working along the board, and in each cell it tries placing a mine, then it continues to solve the board. If that doesn't work, it backtracks to here and then tries as an empty cell, and then keeps going forward and so on. So it doesn't really use much logic, it's just working along the board in turn. By using the probabilities, we can say, well, actually the first thing we're going to do is find the cells that's either most likely to contain a mine or least likely to contain a mine, and play that one first. And we can see if that makes it any better. However, we need some measure of betterness, because otherwise we don't know if it's better. So we could use time, but the problem with seeing how much time it takes, it's going to be quite dependent on how well we code our algorithms. What might be better thing to track is how many wrong turns we make, and if our new version makes less wrong moves than the original one, then it's probably a good technique to be using. So let's add that in first of all. So at the moment our brute force class returns a boolean, so what we're going to need to do is change that to return an integer, which will be the number of wrong moves. Because it's a recursive function, we'll need to maintain some state of how many wrong moves we've made. So the way we can do this is we can create a new function, which is going to be our brute force function. That returns an integer. And within that we have a new variable for the number of wrong moves. Which we're going to return at the end. And then what we can do is we can pick up this entire function and drop it inside there as a local function. Work. Doesn't really matter what it's called. So we just need to call that once. So then the only other thing to do then is start incrementing this value. So we can do that. If we did it here, that would track the number of times we couldn't tell whether a cell contained a mine or not, which isn't quite what we want. What we really want is the number of times we have to undo a move because we've done something that's not valid. Yeah, so that's just, I think that's just going to be like there, and the same thing down here. So if we made a cell a mine and the board no longer valid, then we've made a wrong move. If we made a cell a mine and it was valid, we let our children continue. So we wouldn't class that as a wrong move just because. Is that right? Yeah, I think so. I think it's only when we backtrack from the leaf of a tree because we've made a mistake rather than the intermediate nodes. So I think that's the right thing to do. So then we just need to change our calling for code. So this is now returning the number of wrong moves. So we can just display that. We may as well just put that in a message box. Okay, just make sure that still works. So if we click that now, oh, that wasn't very successful, was it? We need to actually include the number. That might be a bit better. Didn't crash anyway, that's a good start. We also don't actually know what reasonable figure is going to be, but number of wrong moves 175. Okay. Okay, and the second time it's 0 because there are no moves left to make. So maybe we also need a button to reset the board. clear maybe. Clear. So that'll be 300. Clear button. So to clear the board, we want to reload our file. So let's into its own function. How can we do that? So this is the code that gets called when the form starts. First loads. In there. I know why I couldn't do that. It's because they're read only. So okay. So when we click the clear button, we also want to load the file to put things back to how it was. So we start off with a new game object and a new drawer, and then we need to update this screen. Yeah, so when we click the button, we call load file. Load file creates a new game object, loads in the file, and then clears the screen, draws the initial value. That should work. Why can't we see the button? What have we missed off? Clear button. That's with 200, so that volume must be 400. So I think that button's been added underneath that one at the moment. That's better. Yep. Perfect. Okay, so now we can add another button which is going to solve it using brute force, but this time using our probabilities. So what we can do is we'll do the same thing again. And this time we call it clever brute force button. Let's put the word clever on there for a minute. And now we're at 500. So this is going to be very similar to our brute force button. Only this time, instead of calling brute force, we're going to call clever brute force, which doesn't exist yet. So I'm just going to create that. So what we do is we'll start off with just copying our initial one, clever brute force. And there's two changes we're going to need to make. First of all, which cell we're going to pick next, and secondly, whether or not we're going to play a mine or empty first. Because if we think, so we pick the cell that's going to be the most likely one to be correct, and then that might be most likely because it's going to be a mine, in which case we play a mine first. So instead of get next unknown cell, get most likely. So what did the other? Okay, so let's copy that to start with. So let's calculate the probability. So what we're saying is we're going to for every unknown cell, we're going to calculate its probability. And if you remember before building, yeah. So if you remember before, we returned a value between 0 and 1. So 0 means no mine, 1 means it must be a mine, 0.5 means we don't know, and then we've got values in between. So the best cell to play is the number that's going to be furthest away from 0.5, because that means we've got the most certainty we know the value is. So what we can do is if we subtract, so at the moment our number's between 0 and 1, so if we take 0.5 off the numbers, then they become between minus 0.5 and plus 0.5, and then if we do an absolute around that, we'll have values up to 0.5. I think that should work. So we're going to subtract 0.5. And then so now we've got numbers between 0 and 0.5, and the closer to 0.5 it is, the more likely it is that we have the correct value. So we need to keep track of what is the best value. So the best one we start off with is 0, and the best location will be we don't know, so that's that. So at the end of it we're going to return our best location. So here we're going to say if the probability we just calculated is better than our best probability so far, then our best probability is now that, and the best location is now that. And we've got a problem with the types. Decimal, oh, but yeah, let's be a decimal. Because we, right. Okay, so what we can do though is we know. No, that's fine, I think that works. What we could do, 2 stages, we could calculate the probability first of all, and then we can do our adjustment on it. Because then we can say if the probability is either 0 or 1, then we're not going to find anything better than that, because that's our range is between 0 and 1. So we can just return at this point and not bother calculating the probabilities for the rest of the board. Okay, and we're going to leave that 9 as well. So then up here, so that's going to give us the best cell to use, and then we've got to decide whether we're going to play a mine or not. So if the probability for this cell is bigger than 0.5, we need to play a mine. So we calculate this probability, and then just say, so that's the probability for the cell we're going to use, and then say if probability is greater than 0.5, then we're going to play a mine, otherwise we play empty. Oops, come on. And then down here we want to make sure we do the opposite. So it'll be empty or mine. So at first this doesn't seem particularly intuitive, so we could have a really high percentage chance that it's going to be a mine, let's say 0.9. So we play a mine, and then that turns out to be wrong. And so I was thinking about this, is do we then want to try playing empty in that cell, even though it's really, really unlikely to be an empty at that point? But I think we do have to, because as soon as we played a wrong move, it means that one of our decisions somewhere was wrong, and so we do need to definitely try the opposite one. So I don't think there's a better way of doing that. So let's try running it. Okay, so that's 448, which I think was worse. So Vision 1 was 135. So the new, oops, yeah. So our probability version is actually worse with this particular board. Let's try it with a, which game was that we were using? That's the complex game, so let's try the simple game. So the simple one's normally 368, and now it gets it right first time, which is good. So it seems to be dependent on the board whether or not using probability helps or not. Let's go back to the complex one again. So one thing I was wondering was when we pick the most likely cell, is maybe we need to add a bit of randomness in here. So do we do that? So if we had several cells with the same probability, we could pick one of them at random. Because at the moment we're always going to pick the first one. So we could do that simply by traversing the board in the opposite direction. So if we just do something really simple for the moment. What's going to be the easiest way to do this? And it's kind of, oops, so 4R for reverse loop. So the row number of, oops, we copy that logic in. So this will do the board backwards. So then if we can just say if rmd dot next equals 0, and we go that direction, else we go this way. I haven't tried this before, so I think this will work. It's not very nice code, but so that's going to pick a random number between 0 and 1. So that should toggle each time, well, 50% of the time. So in that case, we're going to look at the last cell first and go that way. Otherwise, we start at the first cell and go that way. So this is only going to make a difference if there are two cells with the same probability. We shall see. It might make things worse. So, oh, 254. So it's still worse than not using probability, but it's a lot better than before. And let's just try the other board again. The simple one. So we've broken that. No, that's still okay. That's interesting. Something we have broken is it now doesn't solve the remaining two cells. So using this probability house, so the other change we could make is we could add a bit of tolerance around here. So we could say the probability has to be more what though? More than could be more than a random amount more. So we could say the probability's got to be more than the best probability plus don't want very much. So maybe that. So 0.001, 0.1 or 0.2. Same down there. I wonder if that's going to end up with a integer. So it did make a difference, but not much. Right, well, I think we've got to the end of where we need to get to anyway. So we've added some code for solving the board using brute force. We've come up with a form of measure to see whether using brute force is a good idea or not. Well, using probability to help with brute force is a good idea or not. And we've come up with a way of working out the probability of each cell. So maybe there's a better way of doing these probabilities. Maybe it's straightforward when you've just got one cell to take into account, but when you've got a cell affected by multiple neighbours, maybe doing the average isn't the right way of doing it. So there might be some improvements around there. And then there might be better ways of applying that algorithm. Certainly adding this element of randomness seems to improve things. But it's quite strange how the different games have different results, and that the very simple game where I guess you haven't got many options, it can't go wrong really. So with the more complicated game, there's less cells maybe on the board to start with, and so there's more opportunities to go wrong. Anyway, it's been quite an interesting sort of diversion, and I think that's it for now. Thank you for watching.